this theorem that I was referring to earlier. So this is known as Corso-Ele theorem. I'm not sure I'm pronouncing his name correctly. Corso-Ele's theorem. So what does this theorem say? Okay, so here's what the theorem says. The theorem says that given a formula in MSO2, monadic second order logic 2, and we have a graph. It's an errand vertex graph, and this vertex graph in fact is provided such that it fills in all the free variables in psi, right? So no so the formula phi is allowed to have free variables, right? You know, the vertices of the graph, the edges of the graph, and so on. So G provides all those free variables, right? So that once I give you G and I give you phi, there are no free variables, everything is defined, and the formula is well defined. And now the question of whether this formula is correct or not is well defined. And furthermore, G has bounded tree widths, T. Then in this case, one can decide whether or not this formula is satisfied, and this can be done in time, which is depends on the formula size, that essentially its length when you write it out explicitly, and T, the tree width of the graph, times n, where is the number of vertices of the graph. Namely, it's a linear time algorithm in the number of vertices of the graph. So this is, as I said earlier, quite a surprising result. Okay. Now, what's the next step? Okay, so to see how to use this formula, maybe let's see a bit more example of how to write interesting formulas. So consider again a set of subset of vertices, and you would like to check whether the set X is independent. Well, that's quite easy, right? Because this is just going to say for any two vertices, for every uv in X, we have that adjacent uv it doesn't hold, right? So negation of that. Just use the overline thing, right? So clearly a set X is independent in a graph if and only if no pair of vertices are adjacent. Again, adjacent here is just the primitive function that tells us whether or not U and V are adjacent. I should say, by the way, that I'm pretty, I'm pretty shallow. I'm not going into all the exact detail of how to write the formula and so on. The books goes into more low-level details, but I hope that things are kind of clear. Okay, once we have independent, then we can do things like asking whether, if I give you a set of three sets, do they partition the set of vertices? So partition of x1, x2, and x3 is going to be, well, those three vertices are partition of the vertices if what? If for every vertex in the graph, it's belong to one of the sets, right? So, in fact, let me write it here. For every vertex in the graph, V belongs to x1, or V belongs to x2, or V belongs to x3. Okay? So, so we need that for every vertex it belongs to one of the three sets, and of course we need that it doesn't belong to the other set. So V is not in x2, and V is not in x3, right? And we are going to put a big parenthesis on that. So filling in the formula, we get this formula here, which essentially says every vertex in the graph must belong to one of the sets, and it doesn't belong to the other two sets, and you just go over the possibilities. This is a well-defined formula, so it tells you whether we have a partition. Now we are done, right? Because you can now check like recolorability, right? Recolorability of a graph, right? What is recolorability? Well, there exists set of vertices x1, x2, and x3, right? Subset of the vertices of the graph, such that what? They form a partition, right? So x1 and x2 and x3 are all the vertices colored by 1, 2, and 3, respectively. So we require that x1, x2, and x3 form a partition, right? And now we just need that each color class is independent, right? So independent of x1 and independent of x2 and independent of x3, right? So all those three together, together with the partition condition, implies that a graph is recolorable if and only if this formula is satisfiable. Now notice that this immediately you can plug it into Carousel theorem and get immediately that there is a linear time algorithm for it, right? The linear, it might not be great, but it's there because we don't really know the function. But in many of those cases, of course, doing the dynamic programming explicitly for the problem would be more efficient. But as the book says, for many of those problems, you can think about Carousel theorem as an existential tool. It tells you that there exists a linear time algorithm, and then you can go and look for this more efficient algorithm and fill in the details. Okay, so let's see another example of this stuff, which is interesting, which is Hamiltonian cycle, right? So we need to do it in several steps. The first step is going to, for a set of edges C, subset of the edges, subset of the edges, we want to write connectivity of E. So what is going to connectivity of C? This is just going to be the condition that C, the set of edges, form a cycle, form a connected graph, and we already saw how to do it, right? We know how to do connectivity. We just need to write it for the slightly different version. So again, we look on any subset of the vertices, and we ask for this condition of, we ask for this condition that if there exists a vertex if exists a vertex in Y and another vertex not in Y, then this is implied that there is an edge in C that complies with this. There is an edge UV. There exists an edge UVA such that U is in right, such that U is in Y, V is not in Y, right? Again, there exists an edge in the cut, and it it's a real edge in the graph, right? So incident U is incident to this edge UV, and V is incident to this V is incidental to the edge UV. Right? I kind of wrote it wrong in the sense that instead of UV I have to use the variable E, but it doesn't really matter, right? Again, incident just means that this vertex is incident to the edge, right? So this we already saw, right? This is the connectivity formula that verified that indeed a graph is connected. Okay, the next primitive we need is the degree 2 primitive. So the degree 2 primitive give a vertex in the cycle C, verify that there are only two edges there are only two edges for which that V is adjacent to, right? So, right, and this is very easy, right? So how would we say it? Well, we will say that there exist two edges, E1 and E2, and for any E1 and E2 in C, right? So for any two edges in the cycle such that they are adjacent to V. So inc U to E, so E1, right, incidence U, is it U? I think it's V, okay, V, incident V to E2, right? So the edge is incident to both things. Then if this happened, then this implies that for any other edge E3 in the cycle, right, we have the property that if okay, and we also need a condition, by the way, that E1 and E2 are not equal. Okay. So if this happens, this implies that for any other edge in E3 in the cycle, if it's incidence to V, right, then it must be equal to one of them, right? So this is a bit confusing. And I guess it's somewhat different than the way. Okay, so let me replace this by an and, right? So, and for every E3, if E3 is incident to the vertex, then this implies that E1 is equal to E3, or E2 is equal to E3, right? Right. Okay. Right. Okay, and I think that it's important here that the imply is inside the inner parentheses, right? So the outer formula has this outer exist that says, you know, there must exist those two edges that are incident to C, incident to V, and in addition, any other third edge must be equal, that is incident to V in C must be adjacent to it. Okay, now that we have those two formulas, Hamiltonian, you know, checking whether something is Hamiltonian is now trivial or relatively easy, because Hamiltonian of G? Well, you know, all it really asks is there exist a set C, subset of the vertices, such that what? Well, the first thing is we want C is this. Sorry, C is the subset of the edges. Well, we want C to be, you know, to be connected, right? And right, so we require that the C edge would be connected, and we require also, in addition, that for every vertex in the graph, for every V in the graph, the degree of the vertex in the cycle is 2, right? Every edge is indeed adjacent exactly to 2 edges in C, right? So C covers all the vertices in the graph, and it's connected. As such, it's Hamiltonian cycle. And again, now we can plug this into Coeselle's theorem and get that this is can be computed linear time on a graph that has bounded periods. Okay, so one problem with this this Coeselle theorem is that it depends on the size of the formula, right? And writing down explicitly, you know, vertex cover, we know vertex cover of G of size K. Well, the fact that something is a vertex cover is very easy to write, right? We just need to write, so, you know, vertex cover of X, this is a vertex cover of the graph. You know, if for every edge in the graph, right, we have that there exists a vertex U, right, such that incident, you know, U is an edge, a vertex of E, and in addition, U is in X, right? So this is simple formula that says that X is a vertex cover. So that's not a problem. So checking not if there is a vertex cover in the graph is a trivial formula. It's a constant formula, and you can check it in linear time, but that we already knew, right? You can always take all the vertices in the graph. So we need to put down a formula that says, you know, the vertex cover is of size K, right? And right, and it's not hard to write a formula that something is of size K, right? You can write things like, let me write it calculated, size K of set X, right? How would we write it? Well, we will write something like, you know, right, well, there are several ways, but here is one stupid way to do it. You know, you can write for any x1, x2, 2x, xk plus 1 that are in the formula, that are in X, right? And there exists an equal pair, right? For every, in X, either x1 is equal to x2, or x2 is equal, x1 is equal to x2, and so on, right? We can write this, you know, we can write xk plus 1 is equal to x1, right, and so on. So we will get this matrix of size, well, we will get this collection of, you know, k plus 1 squared, you know, pairs, and clearly this formula is correct if and only if the set X is of size K, right? So this is really bad news, right? Because deciding a vertex and you know, I didn't optimize it. There might be a cleverer and shorter way to verify whether a set is of size K, but it's clear that, you know, you cannot really do it in a much shorter way, right? Okay, so so now if I want to write vertex cover of G of size K, right, what I really want to write, the formula for this is, there exists X subset of the vertices such that it's a vertex cover, right? So that VC of X, right? It's a vertex cover and size K, or size at most K of X, right? And that's the formula that says the vertex cover is of size K, but of course this is really bad, right? Because this formula length is going to be something like O of K squared, and as such, the running time we are going to get is going to be some terrible function of, the one we plug it into Cortez-Selle theorem, it's going to be a function of size, that depends on K square and the band, the tree width of the graph times n. And this is a very weak result. We know much better algorithm already for, vertex cover of size K, right? So really what went wrong here is that the size condition was hard to capture, right? So we want something better, and it turns out that you can have an optimization version of Cortez-Selle theorem, and what do I mean by that? Well, you can write down a formula with, several parameters, x1, x2, to xk. And now we can do something like linear programming, right? We can have a target function that depends on the sets. Right, on the sizes of the set, and this is a linear function and we would like to minimize it. Okay. So the optimization version of Cortez-Selle theorem says that you can solve this optimization version, right? You can compute the optimal solution of minimum price. If the formula is satisfied, you can find the satisfying assignment of minimum price, and you can do it in the size of the formula, which which reduces vertex cover evolve to constant size of inside of K squared, so it's a much better result. And to see that, just remember that in our case for vertex cover, we have only one parameter, and the function is just going to be the size of this set, right? So it's a trivial function, and as such, this is simple. So this is the optimization version of this function. Okay, so this concludes our this part of the lecture on Cortez-Selle theorem. As I mentioned earlier, this is, by the way, corresponds to section 7.4 in the book. This is Cortez-Selle theorem. But let me again emphasize that this is to all practical purposes, this is an existential theorem. The fact that there is a good algorithm, there is a linear time algorithm using Cortez-Selle theorem, just means that it exists. Finding a more efficient algorithm usually requires working directly with the problem, but still it's kind of an amazing theorem. And let me mention maybe another interesting thing that so there is more on this stuff, right? You can look it up on Google. So for example, you can think about the same kind of formula, but now, unlike in Cortez-Selle theorem, you allow the graph to be any graph, right? You can write a property. It just says, give me the graph that have this property, right? And of course the problem is, so this problem will become much harder, right? In particular, if I give you a formula, even in MSO 2, right? And I ask you, is there a graph that fulfills this formula? This problem becomes NP hard, which is not difficult to see, right? Because we already saw that we can do you know, well, it's in fact not obvious to see, right? So in fact it is surprising. Let me repent what I just said. So it is not surprising that it becomes much harder when you ask the existential question, and somehow there are results that says that a problem is decidable. The existential question over MSO2 formula, the existential question whether there is or not a graph that fulfills this formula, this question is decidable if and only if the graph classes you look on are bounded trivet. Okay, if you're interested in more details, you should look up on Wikipedia.